in particular, what I'm going to talk about today is joint work with Juan Esteban Rodríguez Camargo, and essentially is a consequence of conversations that I had with him in the last 4 weeks. So I guess it goes without saying that this is work in progress and that you have to take some of those statements with a grain of salt because, well, okay, the details are far from being checked, but they have some reasonable shape. So I guess if I had to summarize our conversations in the last 4 weeks, I could refer to 2 movies. The first movie that would illustrate the first week would be Miloš Forman's One Flew Over the Cuckoo's Nest. And the second movie for the second week will be Dr. Strangelove, but especially the second part in the title, which is or how I stopped, how I learned to stop, how I learned to stop worrying and love the bomb. And so what is the, so the question, what is the bomb here? So the bomb is this massive piece of mathematics that came out recently and which is called Lucas Mann's thesis, in which he establishes that a bunch of beautiful results, which basically say that you can do now with L equals P what you could do before with L different from P, which is kind of amazing because it was already amazing for L different from P in Scholze's et al. Cohomology of diamonds. So unfortunately, I'm still integrated only by parts in this congregation of 6 functors, and so I would be completely unable to give you detailed statements about these things and how they work. So I'm instead going to focus on some of the consequences of this work. And so what Juan Esteban did yesterday was to discuss the locally analytic setting in which many of the results were inspired and were very often consequences of this very beautiful work of Lubin-Tate on locally analytic vectors in completed cohomology of modular curves. So today I'm going to do something very similar, start with some beautiful recent paper of Hansen and Mann, with a pretty intimidating title on the other hand, and try to add epsilon to it, but I do not specify whether epsilon is positive or not. I guess you all know that all the notations from Juan Esteban's talk yesterday, isn't it? But let me briefly remind you some of the key features. So we have a finite extension f of QP, and we have another large coefficient field, which is also a finite extension with residue field K. Well, most of the time I'm going to be interested rather in this finite field, but there will be some statements in characteristic 0 for Banach representation, so I prefer to have this L. And now there are 2 groups associated to this F. There is G, which is GL2F, and there is D star, where D over F is a quaternion division algebra. And the main player here is this infinite level Drinfeld or Lubin-Tate space, which was denoted by M infinity yesterday, and which has this amazing property that it's a torsor, Proetal torsor for 2 different p-adic Lie groups over 2 very simple rigid analytic spaces, which is very surprising to say the least. So this P1 is just P1 over C seen as adic space, and this is omega, which is P1 minus P1 of. So this is Drinfeld's upper half plane, and this is just the adic projective line. And here the Galois group is D star. So these are Proetal torsors. So here C, let me fix it once and for all, is the completion of an algebraic closure of F, but actually everything I'm going to say works if C was just an arbitrary algebraically closed complete extension of F. So in some sense, the holy grail here is the complex R gamma M infinity with coefficients K or L if you want. Try to understand the cohomology groups of this as a representation of the triple G cross D star cross Galois F. So for the experts, so in 6 functor formalism, that means apply F upper Schwick to the board. So for the experts and only once and for all, because I don't want to have painful questions after this, why I put a Galois F here and not Veil group, I'm implicitly taking quotients by suitable central subgroups in G, D star, and M infinity, so that the Veil-descent datum becomes effective. I prefer to work with Galois representations than with Veil representations, but this is a purely technical feature which you may freely ignore. And so you have these complex representations and you want to know what this is. Well, in degree 0, this is well known by work of Straub. And it's not very interesting because it is related to characters. So it encodes local class field theory. Well, I mean, it is already interesting, but we want GL2 and D star. In degree 2, this is 0 because this is a perfectoid Stein curve. So the only interesting group is H1, but this is a completely unmanageable thing. And unfortunately, we don't have any reasonable conjecture about the shape of this. I mean, all conjectures that we could make were false for trivial reasons. And so there has to be some funny thing that is happening with this cohomology group. But as usual, when you get stuck, there is Scholze who comes and tells you what to do. So he managed to cut out the pieces in this huge representation by putting an extra input, which is a smooth representation of G, or a complex of such. And what he did was to consider pi as a constant sheaf upstairs and then descend it along this G torsor. So you will get some sheaf on P1 with extra structure, E star and gal F, or a complex of such things. And then you can define this JL of pi, which is R gamma P1 F pi. And now this has an action of D star cross gal F. And it's really important to remember this Galois action. You will see why maybe at the end of the talk. So then he proved the following theorem. That if pi is admissible, then JL of pi is admissible. So this has to be interpreted. Cohomology groups are usual admissible smooth representations. And moreover, and this is the key point, if I tensor JL of pi with OC mod P, this is almost JL of pi tensor OC mod P. In other words, the cohomology of F pi tensor O plus mod P. So if you are familiar with Scholze's work on the rigid analytic varieties which are proper, this is telling you, roughly speaking, that this F pi behaves as if it was a local system of finite rank on this proper rigid analytic variety, which is P1. This is, of course, not the case, but still everything behaves as if this was the case. So now there are two basic questions. Well, I mean, there are many basic questions, but there are two that I want to discuss today. The first one is, can you have some vanishing or non-vanishing results for this functor? If I give you a pi, can you tell me whether for some subtle or not so subtle reasons, JL of pi vanishes or not? And can you read invariants, discrete invariants, such as, for instance, Gelfand-Kirchhoff dimension of pi from JL of pi? Maybe in an ideal world, can you recover pi from JL of pi? So this is it's called Scholze's functor, but it could very well be called Fontaine's functor because it's the typical kind of simple thing, which is very easy to define and impossible to compute. So even for a parabolic induction, for instance, I mean, the situation is already pretty complicated when f is equal to qp. If you take a parabolic induction of the trivial character, say, I have absolutely no idea what this JL1 does to it. It's a pretty sophisticated representation of D star, which for obvious reasons, in some sense, is of infinite length. So it's a bit hard to describe. I guess we only know the Galois action on it. And that one is not very interesting. So yeah, I mean, it's very easy to to ask these questions, and then it becomes a little bit harder to answer them. But then there is recent progress by Hansen and Mann, they use this formalism of six functors to actually get some very interesting results about this JL functor. I want to start by addressing the first question, the vanishing result, which I find to be the coolest in our work, because it doesn't really follow from this paper of Hansen and Mann. So let me start by briefly recalling what was known. So JL vanishes in degree 3, at least 3. Let me say for general reasons. Am I writing too small, or is it still? No? Okay. For general reasons, namely cohomological dimension estimates due to Huber and Berkovich. I mean, this was also proved by hand in Scholze's paper. And if you work with GLN, then the bound is 2n minus 1. So really the first interesting cohomological degree in which you don't really know for free vanishing is 2n minus 2. And so now let's specialize to n equals 2. Then there was a very nice paper of Judith Ludwig, in which she proves that you have vanishing for JL2. So this kills all parabolic inductions. And because of part 1, it's also going to kill twists of Steinberg representation. So you're only left with supersingular representations. Now, as usual, supersingular representations for GL2QP, they are known, classified, and for GL2F, it's a complete nightmare. So it's not at all clear what to do. Now, if F is equal to QP, there's a very nice paper of Hu and Wang, and there's some independent work by Hansen, which shows that JL2 kills supersingular representations. Well, maybe with some mild assumptions. In this paper, for instance, you have to exclude maybe 4 or 5 supersingular representations for each prime. There are some non-generic ones, which kind of escape the method. Maybe I should mention that Ludwig wrote after that a paper with Johansson, which generalizes this sort of result to GLN, and they get very strong vanishing results for JL applied to suitable parabolic inductions, not all of them. And then there is this paper of Hansen and Mann. And I will only state the very last result they got. It says something like JL4 kills all infinite dimensional, irreducible, admissible representations of GL3F, which are not supersingular. So it's some sort of analog of this result of Ludwig for GL3. So when you look at the proofs of these results, it's actually fairly amusing to see the variety of methods involved. So here, the key point is the study of this M-infinity modulo de Borel subgroup and proving nice results about the geometry of this space, in particular that it is a perfectoid space and it has a nice map to P1, that the map from M-infinity to P1, which obviously factors to M-infinity mod B, actually has some nice properties. Here, they use the method that was explained in Andrea Dotto's talk on Monday, which originally goes to Breuer, Herzig, Hu, Mora, and Schran. We got them all. And it's a very involved mixture of local and global arguments. And here, it's a little bit similar to this one, but with some extra input coming from the six-functor formalism, in which they establish some sort of QNet decomposition for these representations when you know that you have parabolic inductions, and then you can combine it with the classification due to Herzig of irreducible admissible representations of GL3F. So it looks like, well, I mean, it looks strange because you have clearly a statement which is behind all of these things, but which is not proved in any uniform way. Okay, so here's the theorem. Well, as I said, almost theorem. For any pi admissible of GLN, GL2n minus 2 pi is finite dimension. And moreover, it vanishes if pi has no finite dimensional quotient. Okay, which of course happens very often, in particular when pi is supersingular, this is automatic. So this shows that JL2n minus 2 kills all supersingular representations, and it actually gives a uniform proof of all these results at the same time. And that also shows that you can drop this hypothesis here, not supersingular, and some of the genericity assumptions in this result here. However, we do not recover the refined version of Judith Ludwig's paper with Johansson for GLN, because they have much, much better bounds for certain parabolic inductions. I mean, as one says, nobody's perfect, right? Okay, so how do you prove something like this? Well, you go back to n equals 2, and you remember that this JL2 is some H2 of a curve. Okay, when you have a curve, as one would say, there is no alternative. You use Poincare duality for the curve. You want to prove vanishing of H2, so you compute its dual, and then it will become some H0 of some dual sheaf, and you hope that this one dies. Similarly, if you want to prove vanishing of H2 for Galois representations, again, there's not much to be done. You use state duality to reduce vanishing to vanishing of H0. So this is the type of thing which hides behind this statement here, except that you have to be careful because you need this duality result. Okay, so and this is where we got really very much inspired by this paper of Hansen and Mann. So let me first tell you what they proved and what you have to do to add in order to get this result. So as I said, this functor is defined on smooth representations. So if you want to say something like this JL is compatible with duality, you might be interested in having a duality which preserves this category of smooth representations, at least at derived level. So there is a smooth duality, or if you want contragradient, due to Scholze, which is very easy to define actually, but only at derived level. So derived category of, let's say, smooth admissible representations of any p-adic H. Okay, so what does it do? Well, you take pi and you smoothify it, or rather its dual. So this is the naive dual, just k-linear dual. And this smooth thing, well, you don't really do only the stupid thing of really taking smooth vectors, but derived version of smooth vectors. In other words, you can rewrite this as colimit over compact open subgroups k of H of R gamma k with values in pi d. And of course, it's continuous cohomology here, and this has to be interpreted as profinite thing or solid or whatever you like. And so Scholze shows that this has some excellent properties. In particular, if you apply it twice to pi, you get pi again, and so on and so forth. So I'm going to call this just pi check, the smooth dual of pi. Okay, and so it's a fact that, as I said, that the cohomology groups of pi check are still admissible, and everything works well. And so now you can formulate a compatibility between this JL and this smooth duality, and this is, I guess, one of the main results, or maybe the main result in this paper of Hansen and Mann. which says that JL is compatible with smooth duality. Except that you have to be a bit careful. So the correct formulation is that I take JL of pi, I take its smooth dual with respect to the action of D star, and this is naturally isomorphic to JL of the smooth dual of pi. And then there is a Tate twist by n-1. So this is for GLN. Tate twist. And then there's a shift by 2n-. Okay. So this is very nice because now you may try to implement the strategy I said. If you want to prove vanishing results for or finiteness results for JL in degree 2n-2, you may try to apply cohomological HI, let's say, to this kind of equality and then study what's happening. Well, as I said, this is now a complex of smooth representations, smooth admissible representations of G. Okay, so I can still apply JL to it. I've just defined it downstairs. Is the smooth dual of pi? Yeah. Except that now you have to be careful if pi itself was a smooth representation concentrated in 1 degree, or let's say degree 0, this is no longer concentrated in degree 0. Okay. So what is this guy here? Well, I don't really know, because after all, this was obtained by applying a composition of 2 derived functors to. So there is indeed a spectral sequence, which most likely I have difficulties remembering because there are some funny signs involved in there. Well, with a bit of luck, it should be something like Si of JL minus J of pi goes to and I have to tell you what is this Si. So here, by definition, Si of, let's say, of anything is HI of small dual. Okay. So this is just the usual spectral sequence for hypercohomology, except that since some things are contravariant, some covariant, it involves some funny twists, some funny changes in signs. And there's a similar thing computing. Well, the other side, HI. Well, and now you start staring at these spectral sequences and you realize that already for n equals 2, which I'm very happy to assume, this becomes intractable. And let's see why. Well, because you want to apply cohomology here. So this will be HI here is HI plus 2n-2, maybe even H0 if you want, and H2n-2. But then you have to deal with these terms in the spectral sequence and you have to understand them. But if you look at the spectral sequence, you will see that in the degrees that we are interested in, they will involve something like JL2 of pi, which you don't know much about, but you hope that it will appear among your short exact sequences or whatever follows from the spectral sequence, and you want to kill that. But then there are also many other terms involved, like S1 of JL1 of pi, which you don't really know much about as well, and so on and so forth. And the same thing happens here. So, well, it just becomes a complete mess. So, yeah, it's a little bit depressing that such a nice result cannot give you for free this vanishing. So, well, I don't know what's happening in Germany, US, or other countries. But in France, if you look for movies in the evening, sometimes they get interrupted and there's a message of the, I'm going to write it in French. I'm slightly adapting the official message. There is also a version with well, any of this. So you see, for instance, now if you apply H0 to this, well, maybe I don't want to apply H0. Maybe I want to apply H2 and minus 2, and then there is some funny thing happening. But anyway, JL2 and minus 2, if you look at how things work, and you are happy with changing signs in your head, it should give something like JL0 pi dual. You see that minus 1. And now there's something really fun happening. Now let's try to come back to Earth. What is this JL doing actually? Well, it was defined as cohomology of some sheaf f pi, which was obtained by descent from the torsor, but actually cohomological descent implies that this JL of pi is nothing but the pi isotypic component, well, of course, in derived sense. Okay, so we are just doing here the good old-fashioned thing of taking pi part of cohomology for L different from P, except that now L is equal to P. Pi star is just the naive dual of pi. No. Yeah. The point being that this itself is not at all smooth. This is a pro-discrete object with a continuous action. So you have to take care of it. And the category is the category of solid representations of G and so on and so forth. I guess you could make sense of it if you just work with pro-discrete things with continuous action of G, but yeah, if you really want to manipulate these objects correctly, it's better to stay. I'm going to come back to this issue. That's a good point. Yes, there will be a remark about this. The question was whether this functor JL is compatible with taking smooth vectors. And I will address this question. So this would be like the analog of the question raised yesterday, is the JL functor on the Banach side compatible with taking locally analytic vectors? To make it short, the answer is yes, and I will add a few details. Yeah. Well, I mean, right, if you compare the two theorems, they tell you that it should be the case. But the funny part is that you can actually prove this independently of the theorems, which is pretty reassuring because I was really afraid at some moment that we were doing something wrong, but actually you can prove by hand this compatibility. So let me go back to this in a moment. All right, so this is the object, but now similarly, JL of pi dual is this one. So if you come back here, this is nothing but G from pi into H0 M infinity K, well, with some funny K twist. But as I said, this is described by Scholze, and it's very easy. And then when you home from something admissible, you kind of see very easily that this thing is finite dimensional. So one has to be worried a little bit here because there is the difference between GL2 and SL2. There are some funny inductions appearing here. And this is precisely why I took quotient by a certain central subgroup in G, so that I make sure that this stays finite dimensional. I want the restriction of something admissible of GL2 to be admissible for the group I'm working with. And so I need to do a slight twist, but this is nothing serious. This is just called Pontryagin duality. Pi is its own continuous. Pi is the continuous dual of the naive dual. Okay. So you get this kind of statement, but actually you get even very nice formulas, which I would have never imagined they were true, actually. Let's take n equals 2. And instead of taking cohomology in degree 2 and -2, take it in degree 1. So what you will get will be the following nice formula. Well, okay, there is some junk coming from certain spectral sequences related to H0, which I'm going to ignore here because that's not the point. But this is really G from pi into the colimit of H1 et al, Lubin-Tate n, coefficients k, maybe twisted by 1. So here is the nth Lubin-Tate space, which is obtained simply by taking the quotient of M infinity by suitable congruent subgroups in GL2. And of course, it can be described in a different way. And now comes the miracle. If you know to say something non-trivial about this guy, about GL1 of pi, then you will say something non-trivial about this representation. And I would have never imagined, for instance, that this thing here is independent of C, and that it is a finitely generated module over the USL algebra, because after all, it's just the dual of something admissible for D star. I mean, this just seems impossible to prove by hand. This is a smooth representation of GL2 for obvious reasons. It's by design, but you can hardly imagine something less admissible than this representation. Because if you take, let's say, invariance, even under GL2ZP, you end up with something like H1 et al of an open unit disk with coefficients FP, say, and this is well known to be humongous and to depend on C. But somewhat miraculously, if you home something admissible into it, it becomes pretty reasonable. And here we crucially use admissibility of pi. Yeah, so for instance, once you know that GL1 of pi is non-zero, you will, and pretty big, you will also know that pi actually appears in the cohomology at finite level along the Lubin-Tate tower. Well, maybe I should stop this with this interlude and maybe address the question that Joaquin raised. So remark, if you combine theorem 1 and that is theorem 1 and this is theorem 2. They suggest that, well, after all, if I take smooth vectors here, I'm supposed to find the one there. So I'd better have the same thing here. So again, you have to be careful here. I'm really taking derived smooth vectors, that this is really JL of pi dual G smooth vectors. And this is exactly the analog of what Juan Esteban was talking about yesterday in this new setting where you work with mod P coefficients. But actually, this is surprisingly tricky to prove by hand. You can do it. In particular, you never prove this kind of statement by working with mod P coefficients. You always use these comparison theorems like the one I stated before to pass to O plus mod P coefficients, where life becomes easier in some sense. And then you only get almost statements and you have to go back to real life. But even when you take O plus mod P cohomology, you still have to do something. And there is something that has to be done is the same argument that appeared yesterday in Juan Esteban's talk, namely this result of Zavialov that if you take classical smooth aphenoid and you look at its O plus mod P cohomology, this is very well behaved. And so in particular, if you have a p-adic analytic group acting on this smooth aphenoid, this O plus mod P cohomology, well, up to some almost thing, the action of the group factors through a finite quotient on the cohomology groups with coefficients in O plus mod P. So yeah, I mean, this is something which can be proved by hand, independently of p-adic formalism or whatever. And so I guess it also shows that if you know how to prove this theorem by hand, you will also get the one upstairs simply by applying smooth vectors with respect to the action of d star to this equality. But of course, this would be a lie because, I mean, to prove this, you do exactly the same thing as they do upstairs. Maybe the only difference, and this is something that Scholze noticed, is that actually to prove this, you only need the formalism for the projected for the morphism, which is just the projection of the projective line. This is unfortunate. So the map from the projective line to the point, okay, very nice classical rigid analytic varieties. You only need Poincare duality for that. While there, you actually need Poincare duality for stacky things like a point modulo p-adic Lie group towards point, which in some sense is Poincare duality for p-adic Lie groups, but in this geometrized setting. However, it's a bit tricky to realize that it's not so easy to implement this strategy. So, well, maybe if you ask me at the end, I can tell you how you can write 3 lines which make no sense and which prove this. And then you have to spend many, many pages to unravel in Lucas' thesis to see that everything makes sense and that it lives where it should live. But actually, the idea is very, very simple. There's not much to be done once you have this very powerful machinery. Okay, so I don't have too much time left. So let me focus on some applications of this. But unfortunately, here I'm obliged to stick to GL2 precisely because we don't have strong vanishing results for GL3, for instance. But I mean, these kind of things are already pretty interesting for GL2, so it's not too bad. So here's a general conjecture that Hansen and Mann make. They say that the Gelfand-Kirchhoff dimension of JLI of pi is always bounded by the Gelfand-Kirchhoff dimension of pi for any pi and any I. Of course, my pi's are always admissible. So let me just briefly recall you what this GK of pi is. Well, in brutal form, it's this thing. Oh, sorry. Yeah. Then it would be just k to the p to the n times log pi, which would still make sense if k was an integer, over, well, and this is where I'm certainly going to, it's something like this. No, n times log p. Yeah. So roughly speaking, if you look at the dimension of invariance under this p to the n power of k, it's roughly speaking a constant times p to the n times the Gelfand-Kerlove dimension. So let me write this in a more human form. But you shouldn't really take this for granted because it's not really true, at least not in the state of, just a second. K is any uniform open pro P subgroup. Pro P uniform open subgroup of your of the group acting on pi. Okay, and the result is independent of the choice of k. And this is roughly speaking constant times p to the n times the Gelfand-Kerlove dimension of pi. That's about how you should remember about this and not the logs and things. But we don't really know how to prove, for instance, that this thing divided by this thing actually converges. So we only know how to do it once we take logs. But you will hear a lot more about this kind of stories in Marie-France Vignerat's talk tomorrow. Now, of course, with this kind of definition, you cannot do anything in practice. But fortunately, this is actually related very simply to this smooth duality functor. This is exactly the largest d such that SD of pi is different from 0, and then SD of pi is also d-dimensional. So remember that this SD of pi is the diff cohomology of the complex given by the smooth dual of pi. So now you are in much better shape, because if you know that your JL thing commutes with smooth duality, you can have a chance to control these things. Again, now we have to stick to GL2 because, well, there are still all these nasty spectral sequences, and we only have a vanishing result for JL2. If you work with GL3, for instance, you would still have to have a vanishing result, for instance, for GL1 or something like this. But still, assuming that everything is nicely concentrated, then it would follow that this conjecture is true. But of course, we don't know how to do it. However, for GL2, this is true. So, and it follows formally from what I said before. So the corollary of theorem 2, the conjecture is okay for n equals 2. Actually, for a very long time, I didn't know how to do it, even for f equals qp. And again, it just follows by staring at those spectral sequences and working in the category of admissible smooth representations of D star modulo finite dimensional ones. And then practically all terms in those spectral sequences vanish, except the ones that are interesting. And you actually get something of the form even JL1 of SD of pi is SD of JL1 of pi. In other words, you have commutation of JL with smooth duality in each cohomological degree up to finite dimensional things. And moreover, if pi is Cohen-Macaulay of dimension D, which means that SI of pi is 0 unless I is equal to D, then actually, I forgot the crucial hypothesis, and this is very tricky to check in practice, and JL1 of pi is infinite dimensional. This is becoming very small here, is infinite dimensional, then the two have the same Gelfand-Kerlove dimension. The key is the study of this of these two spectral sequences here. And the point is that in these spectral sequences, the only interesting terms are Si of JL1 of pi, because all the other ones are finite dimensional for, let's say, stupid reasons, because we have this finiteness result that JL2 is always finite dimensional. Oh, by the way, I forgot to say JL0 is always finite dimensional in this setting for really easy reasons. Again, related to this formula, if you specialize it to degree 0, for instance. Okay, so yeah, I mean, the thing works precisely because practically all terms there are finite dimensional, except the terms which involve this JL1 of SD of pi, and the terms coming from the other spectral sequence which involve SD of JL1 of pi. Yeah, well, hopefully. Well, I mean, one of the key points in all this business is that we were trying to get these vanishing results so that we can then do deformation theory and lift information from mod P to the Banach setting. For instance, it was not known, to my knowledge, that if I take an irreducible Banach representation unitary and so on for GL2QP, and if I apply JL1 to this representation, I didn't know how to prove, and at least it was not in the literature, that this is non-zero. But it follows from once you know this vanishing thing, because mod P one knows how to prove things, and then one can lift them, because now what our results say is that this JL1 functor is basically exact up to small pieces. So yeah, most likely all these results are going to pass to locally analytic, but one has to be very careful. For instance, if you do the locally analytic version of that was explained yesterday, and you apply it to a supercuspidal smooth representation, you actually get 0. If you put really the JL with F pi, if you put it with version O hat, then you get some mysterious object, which we cannot describe. But you have to be very, very careful when playing with these objects, because you easily end up in strange waters. Okay, I still have only 10 minutes. So now I'm supposed to tell you that this implies something interesting about the cohomology of Shimura curves. And of course, as usual, this means that I would have to start filling a board with all kinds of objects of global nature. So let me summarize Andreas' talk in a few lines. So application, let's take F over Q totally real. P a place dividing P, infinity a place dividing infinity, very good notation. And B bar over F, quaternion algebras, which are sisters with respect to P and infinity. So what do I mean by this? This is in the sense of Cherednik and Drinfeld. So they have the same behavior outside, the same ramification outside of these two places. At the two places, the ramification is exchanged. And moreover, I ask, for instance, that B is split at P and totally definite. And well, for B bar is the opposite. Okay. So associated to this, we have Shimura curves for the one that is split at infinity, which I already forgot what B bar, or B bar, and Hida sets for B. And so out of this, like in Andreas' talk, you can construct completed, well, it's really not completed, but it doesn't matter, completed cohomology groups, H1 hat for B bar. This is supposed to indicate the cohomological degree that we are looking at. So we are looking at Shimura curves in degree 1 with a cohomology, and here you just have some finite sets. So you just take functions on all of them for B. So these are exactly the same objects that appear in Andreas' talk. And let me remind you that this actually involves the choice of a tame level. And then you only increase the level at the place P dividing P that you fixed from the very beginning. Okay, and there is also a spherical Hecke algebra acting on these things. And here's the theorem. Oh, I forgot to put quotation marks in my theorems. So, okay. They are all of the same sort. Well, I mean, once the vanishing thing is okay, you can drop quotation marks from all the other ones because they are basically just formal consequences of the compatibility with duality. So this is saying that for any M maximal ideal of T with residue field K, which is non-Eisenstein, the GK dimension of H1 hat of the Hecke eigenspaces in the cohomology of Shimura curves is actually bounded by the one for Hida sets. And we have equality if if H0 hat M is Cohen-Macaulay, which unfortunately is pretty hard to check in practice, of course. So let me summarize this result. That's the way I remember it. Okay, so there's this basic conjecture that all these things are equal, and they're all equal to the local degree at P. This is just, you take the completed local, I mean, F index P, and you take its degree over QP. And it is known, and this is a very nice argument that Vitas explained to me a few days ago, that this always has a lower bound. In practice, you prove this kind of lower bounds by using patching and using some non-commutative tricks and things like this. And this involves assumptions on the maximal ideals you take and so on and so forth. Actually, here, there are no assumptions at all. This is always true. And also, the theorem is supposed to work without any assumptions of Taylor-Wiles type or anything like this, simply because we never use them. There is no patched module or anything like this. We just take the local statement and combine it with local global compatibility established by Scholze, which tells you that JL1 of this one is basically this one, up to some, JL1 of this one is this one, good point. Yeah, well, there is a small junk in this issue, but it's irrelevant for this thing. And there is one point, there was a hypothesis there, JL1 of pi is infinite dimensional, so this is not obvious a priori, but this is in Scholze's paper, that if this is non-zero, then this is actually infinite dimensional, and it was basically already in Breuil and Diamond's paper, well, up to some technical assumptions. Okay, so this is basically telling you that every time you can prove something smart on the GL2 of F side, you automatically get it on the D star side, right? Yeah, it's mod P. That's an excellent point, actually. But this is why I struggle to prove statements mod P, because they have much stronger consequences than statements in characteristic zero. For instance, things like this for modular curves are very well. Okay, can be proved independently of p-adic Langlands, let's say, for modular curves. But I still don't know any proof that avoids p-adic Langlands for modular curves or the method introduced by the 5 authors. However, in characteristic zero, you can do this by using the action of the infinitesimal action. But mod P, for instance, this kind of statement, if you know it, if you know that we really have equality here, it actually implies that all Hecke eigenspaces in characteristic zero are non-zero, which is a very strong statement. And it also implies that, for instance, that the dual of completed cohomology is actually flat over the localized and completed Hecke algebra. So there's a lot of highly non-trivial arithmetic information that is hidden in this type of inequality. And as I said, this is always true. If you want to know the proof, you ask Vitas. This is always true and can be proved. Establishing upper bounds is a much harder problem. And so what people do, for instance, what we can do now is take Emerton's result, plug it in, and get the same result for the D star over Q. But we can also take results of Roy, Herzig, Hu, Mora, and Shan, which established that this is less than or equal to this local degree when this thing is unramified and suitable genericity assumptions, and then deduce the same result on the ramified part. One funny thing about this statement is that actually it holds when FP is ramified. And I don't know anything that is done in this direction on the GL2 side. I mean, the methods so far are limited to the unramified case. But still, I mean, there is no miracle in this business. At some moment, you have to prove actually something here. And this is going to be the hard part. What this theorem is telling you is that, okay, if you know here, then you know here. And it kind of, it's a division of labor statement. Okay, so now let me finish in, okay, this is going to be short. So recovering pi from JL of pi. So for a long time, I was convinced that you would be able to, that this JL of pi actually contains all information about pi. And then I started discussing with Vitas in Essen many years ago, and he convinced me that this should definitely not be the case if you see JL of pi only as a representation of D star. Now, it turns out, this is still not written, but again, if you put enough pressure on Vitas, he will explain how to do it. It is known for GL2QP that if you take some, let's say, generic irreducible Banach representation of pi, and you plug in JL of pi, that it will actually factor as a Galois representation of dimension 2 tensor something on which only D star acts. And this two-dimensional Galois representations is exactly what comes from Kolmez's functor. So what this result says is that this JL of pi is powerful enough for GL2QP to encode Kolmez's functor. So in some sense, this gives a hint that if you look at JL of pi as a Galois cross D star representation, you can actually recover pi from it. And here's a, well, I'm not going to state it as a conjecture because I'm not sure I want to see next week on arXiv a preprint whose title is something like the Camargo Dospinescu conjecture is false for trivial reasons. But let me formulate it as the following question. Isn't it true that gal F, so this is a pretty strong question because I'm allowing any F now. So I guess I'm putting a lot of responsibility on my co-author's shoulders. I'm happy to do that. So JL1 of pi into H1 et al. M infinity K is very closely related. I leave some freedom to pi dual. And in an ideal world, up to some Tate twists and junk coming from H0, they should even be equal. So let me finish. I'm only going to take 2 more minutes if Benjamin is willing to do this. So I have no idea how to prove this even for GL2QP actually. But there is a hint that this might be true. This is related to Scholze's functor, but going in the opposite direction. You want to do this construction now, a descent along the other torsor, but things get a lot harder because on the other side, you get Drinfeld space, which is not proper. And all these admissibility results are encoded in the properness of P1. So this is why this is quite tricky. So fact, so this will be hopefully someday written. If P is at least 5 and pi is, no, and V is a 2-dimensional irreducible representation of Gal QP, then hom from V into the completed cohomology of the Drinfeld tower, which is a much smaller piece than H1 et al. M infinity K, or its version with L coefficients. This actually factors as a completed tensor product like this. And this basically shows you that in the completed cohomology of the Drinfeld tower, you see all two-dimensional, well, some genericity assumptions. Let me say generic enough. You see all two-dimensional Galois representations contrary to our previous results, which dealt with finite levels in the Drinfeld tower and which had some assumptions like the Ram, Hodge-Tate weights, and so on V. Now anything will occur, and the multiplicity is the right one, the one expected from the L different from P theory. So if you combine this, yes, now it's characteristic 0. But there is a statement like this, for instance, if V is irreducible mod P, this will still be true without the completed tensor product. This fact plus the expected, but curiously non-trivial statement that the endomorphisms, this is completely ridiculous, but I mean, that's how life is. We don't know how to prove this, that the endomorphisms of JL1 of pi are scalar. Well, it's certainly true for many pi's, as follows from recent work of Hu and Wang, but I don't see how to do it in general, would imply the question for GL2QP. So since I strongly believe in this kind of statement, and since I also strongly believe in this kind of statement, I strongly believe that you would have a positive answer to this question for GL2QP. And now the question is whether this makes sense for GL2F or not. No idea. Sorry about going over time.